Dear Professor and colleagues, my name is Li Yi and come from China. I'm currently a PhD student at the University of Kaiserslautern. Today I'm very happy to make a presentation about my paper with the title, A Case Study on the Part Optimization Using Eco-Design for Additive Manufacturing Based on Energy Performance Assessment. The presentation will consist of 4 parts. In the first part, we will introduce our research background and motivation, as well as the fundamental theory of additive manufacturing. In the second part, we will introduce the methodologies and tools that have been used in the design case. And in the third part, we will introduce the procedure and result of the design case. And finally, we will make a brief conclusion and outlook to the presentation. Generally, the manufacturing mechanisms can be distinguished between additive, subtractive, and formative manufacturing. In subtractive manufacturing, for example, machining and joining, the volume of the workpiece will be reduced due to the scrap. And during the formative process like molding, the volume of the workpiece before and after the processing will be constant. And only in additive manufacturing, the volume of the workpiece will be increased because the volume of the workpiece before the processing is 0. And the change mechanism of the volume of a workpiece is the most important criterion to differentiate an additive manufacturing process from conventional manufacturing process. Years before, additive manufacturing was considered as a more cleaner production technology than conventional manufacturing processes, and the advantages can be, for example, additive manufacturing enables lightweighting and functional improvements of product, has no cutting tools or fluid, and has less material waste, and enables the reorganization and shortening of the supply chain, which will lead to more energy savings. But recent studies also show that there may be some disadvantages for the implementation of additive manufacturing. For example, the implementation of some powder-based additive manufacturing processes require the production of powders, and these processes can be very energy intensive. And also, although during the build process, no cutting tools and fluid are required, but in additive manufacturing, we always need to use subtractive process as post-processing to improve the product surface finishing as well as geometrical accuracy, so the cutting tools and fluid are still there. And also, for some laser-based additive manufacturing technologies, the efficiency of the heat transfer between lasers and the materials is very low. And also in some additive manufacturing processes, the processing time can be up to days or weeks. And longer build time also implies more energy consumption. So conclusion of this discussion on the energy and sustainability performance of additive manufacturing is that the environmental benefits of additive manufacturing should be evaluated more critically. And if we want to ensure these environmental benefits, we have to carry out innovative eco-design approaches. Eco-design for AM implies any type of design in which AM and environmental issues are considered. The most common evaluation tool for sustainability is life cycle assessment, which provides comprehensive ecological performance profiles about the design solution. But for eco-design for AM, LCA can only be executed in the later design stage because it requires very detailed inventory data and it requires the mapping of the entire process chain, so-called Glatt to gate. In this case, we suggest to use energy performance assessment to replace the LCA as the evaluation tool. So the general idea about the approach is that first, we will optimize the product using a generative design approach, which describes the iterative process between lightweighting and fillet element method. And afterward, we will propose different design solutions based on the energy performance assessment as the evaluation tool. we will quantify the energy performance of all design solutions, and we will select the optimal one. The part that will be optimized comes from a conveying system for producing cylindrical rod. As you can see that a cylindrical rod will be manufactured and will be cutted, and it will then drop to the conveying system. The cane plate will rotate clockwise, driven by a chain gear to ensure a constant tactile time, and the diameter of the cane plate is about 100 mm, and its weight is about 433 grams. And the cane plate has been selected as the part that will be optimized. For the design case, we first analyzed the use condition and defined the two load cases, according to which we then carried out 8 optimizations and obtained 8 design solutions, in which the lightweighting factor has been reduced to 0.7. A lightweighting factor defines here a ratio between the reduced volume and the original volume. So the larger lightweighting factor implies more volume reduction. And from the fig on the top, you can also see that the stress and the distortion are increased at first slightly and then significantly, along with the increase of the lighting factor. And these curves shows that the more material are reduced, the more stress and distortion will be there. And these 8 design solutions are selected as the candidate for the first energy performance assessment. For the energy performance assessment, we carried out energy simulation at first, because the experiments are very time and cost spending, so we proposed the simulation approach, and the simulated power curve has been depicted on the right side of the slides. And afterward, we defined the following 4 performance indicators. And for more information and description about these indicators, please see our paper. And since these different indicators have different units, if we want to integrate them together, we have to normalize them. And in this design case, we adopted the min-max features approach, in which the range for all design cases for a specific indicator should be calculated first, and then we will see the indicator for each design case and to compare it with the minimum or the maximum indicator, and then the indicator for this case will be converted into a number between 0 and 1. And afterward, because different performance indicators have different weighting factors, and the normalized value will be multiplied with the weighting factors. The result of the multiplication is the aggregated value, and we will evaluate the energy performance of all design solutions on the aggregated values. This slide shows the result of the energy performance assessment through the pairwise comparison approach. Total energy consumption has been calculated as the indicator with the highest weighting factor. And after the normalization, from the stacked area chart on the left, it is seen that design solution 8 has the highest score, followed by design solution 7 and 6 without significant difference. But after the aggregation of the normalized value with the weighting factors, it is seen that the benefit of the design solution 8 is more significantly. And this implies that the solution 8 has been evaluated as the design solutions with highest energy performance and has been implemented for the application stage. For the production of the optimized part, selective laser melting process has been used. Finally, we can make 2 conclusions based on the case study. The first one is that the generative design approach is a very powerful design tool for product optimization. In our case, we reduced the 70% of the volume approximately. And the second conclusion is that energy performance assessment is feasible as an evaluation tool in comparison to life cycle assessment. And of course, based on the case study, we still require two future works. The first one is that we have to explore more assessment indicators. Well, in our case, we defined 4 of them, and in the future, for other cases, for other design purposes, the energy performance assessment indicators should be defined individually. And second, our work followed the hypothesis that the energy performance assessment can be equivalent to life cycle assessment, and whether this hypothesis can also stand for other more generic design purposes or other cases should be studied in the future work. Thank you for your attention. That's my presentation. For more information about the case study, please see our paper. Thank you.